And let's start talking about magnetism, some of the basics of magnetic fields as well as electromagnetic fields. So a little bit of background information that you probably already know from your elementary school days maybe. All bar magnets have two poles, North Pole and South Pole. So electricity, we had positive charges and negative charges. In magnetism, we have North Poles and South Poles. And then how those poles interact depends on what combination of poles we're trying to interact with each other. So if we have two like poles, so two North Poles or two South Poles, they will repel, whereas if we have an opposite pole pairing, a North Pole and a South Pole, they will tend to attract. Now here's kind of a fun one that hopefully you don't have firsthand experience with. If you take a bar magnet like this one, it's got the North Pole and the South Pole. If I were like crazy strong and angry and I broke it in half, I would have two fully formed magnets, each with a North Pole and a South Pole. It would be impossible, like I wouldn't break this and have like one piece that's just a North Pole and one piece that's just a South Pole. Each of those pieces would have both a North and a South Pole. And that's because magnetic poles always come in pairs. You cannot have a North Pole without an accompanying South Pole. And that's actually a subject of a lot of interest in the physics community and a lot of research that's being done, just trying to figure out, like, can we have magnetic monopoles? Is it possible to have a North Pole by itself? And so far, I don't think we've found it. It hasn't happened yet. So yeah, magnetic poles always come in pairs, right? Now, one thing that we know about magnets then, we know that they then can exert forces on each other because we talked about repulsion and attraction between these different poles. And if we look at what those forces do, we can see that those forces can happen at a distance. Magnets don't only attract or repel each other when they're in physical contact. They don't even have to be touching to have that attraction or repulsion take place, which tells us that magnetic forces are field forces. Now, previously, when we have talked about fields, we've looked at gravitational fields, which all pointed radially inward, and then electric fields, which point radially inward for negative charges and radially outward for positive charges by convention. So with that sort of foundation in mind, let's make the jump over to magnetic fields, which look a little bit different from these two. So, first of all, by convention, the same way that electric field lines show us the direction of force on a positive charge, magnetic field lines show us the direction of force on the North Pole of another magnet. So like the north side of a compass, which way it would tend to point, that's what the field lines are telling us. And when we want to shorthand magnetic field, the variable we use is B. And I don't know why. Maybe there is some language where magnetic field starts with a B, or maybe we're out of letters. I don't know, but B means magnetic field, okay? So we're seeing that these field lines represent the force on the north side, the North Pole of a compass, all right? And so if we were to trace out that field for a permanent bar magnet, what we find is that those field lines always form closed loops. And the direction that those loops point, because like poles repel and opposite poles attract, is those loops always point where they are, the field lines are pointing away from the North Pole and then back toward the South Pole. So the image you see here is just kind of the way that iron filings would kind of tend to align to the magnetic field. But if we actually want to put directions on those field lines, they might look something like this. So notice that for each of these magnets, we're getting these circles, these loops that are being produced. And if we trace the direction of those loops, the field lines are all pointing out of the North Pole of the magnet. They're all pointing away from the north, and then they loop back around in towards the South Pole. Now, I just said that magnetic field lines always form closed loops. That's not readily evident from these drawings because we're sort of limited in terms of like the amount of available space, and we're limited to 2 dimensions. But it turns out if you were to continue following those field lines around, they do in fact like continue back around and connect back up from the north to the south. So even though you can't see that all of these field lines sort of out on the ends there continue around and form closed loops, they do in fact do that. I also want to kind of trace this out for you a little bit in 3 dimensions, because in magnetism, we're going to be thinking in 3 dimensions a lot, and we're sort of limited in drawings to 2 dimensions. So I want you to imagine for a moment that this little box is a bar magnet, kind of like what you see on the right in the images right here, where we've got the North Pole up on the top here and the South Pole down on the bottom. So if we have this 3-dimensional bar magnet and we want to see what its magnetic field looks like, it actually looks something kind of like this. It's kind of like donut shaped, right? So we've got these closed loop field lines circling all the way around our bar magnet in 3 dimensions, again, pointing out of the North Pole and back into the South Pole. The other thing that you can't see from this is that really those magnetic field lines would be like a bunch of nested donuts. So we've got like our one slinky here, but if you imagine like another bigger slinky that goes around this one and continues around, and then an even bigger slinky that goes around them and continues all the way around in 360 degrees. That's really more what this magnetic field looks like. It's just tons of like loops within loops within loops within loops, extending all the way around and then going out like infinitely far. So that's a fun thing to ponder. Anyway, so that's what our magnetic field looks like. Now, just to take a moment to check your understanding, consider this bar magnet right here. Where is the North Pole located? Now again, magnetic field lines always point out of the North Pole and then back into the South Pole. So then looking at this, I can tell that the bottom must be the North Pole of this magnet because that's where my field lines are pointing away from the bar magnet. And then the top is the South Pole because that's where the field lines are pointing back in. Now, bar magnets are good and cute, but there's more to magnetism than just bar magnets. As you saw in your investigation, an electric current also creates a magnetic field, which means all this time that we've been building circuits, we've also been building magnetic fields the entire time. Like anytime we had a current, there was a magnetic field around it. We just didn't know. All right. So electrical currents can also create magnetic fields even in the absence of bar magnets. And so to try to like connect these two things together, what I want you to think about is that all magnetic fields are really caused by the movement of charged particles. And typically those charged particles are electrons. So if we think about a bar magnet, and what's going on down at the atomic level in that bar magnet, each of the atoms in that magnet has electrons that are orbiting around this nucleus. It's those electrons that are creating the magnetic field of the bar magnet. It all comes down to the way that the electron is orbiting around the nucleus of its atom way down in that magnet. And then similarly, when we get an electromagnet or this current carrying wire that produces an electric field, or excuse me, a magnetic field, that again is caused by the movement of electrons in the form of a current going through that circuit. So whether we're talking about bar magnets or we're talking about current carrying wires and electromagnets, in both situations, those magnetic fields arise from the movement of electrons. Wild. All right, so to kind of focus in a little bit more on what that means for bar magnets, all right? So just to provide a little bit of context, in unmagnetized objects, atoms will tend to cluster together and form these little groups, which we call domains. And those domains will have the electrons starting off just orbiting randomly, okay? And as a result, we don't get an overall magnetic field because one domain might have a magnetic field that's sort of like pointing this way, another magnetic field for another domain is pointing this way, and another one's going that way. So they're all kind of canceling each other out. There's no unity, there's no organization, so the magnetic field just doesn't really get anywhere. Right? But if we were to magnetize that object, what that really means is that we're getting all of our electrons in alignment. So they're all orbiting around their nuclei the same way, and that causes the domains to all have magnetic fields that are all pointing in the same direction. And then all those magnetic fields kind of build and add together, and that gives us an overall magnetic field from that object. Now, most materials, their domains don't naturally tend to align. Chaos reigns. But in some materials, which we call ferromagnetic, things like iron, things that can be magnetized, there is more of a tendency for those domains to stay aligned once they've been magnetized. Okay. And again, just an image to kind of help you visualize what's going on here. So we see for an unmagnetized material, we've got these different domains, which are represented by the sort of different shapes, these odd shapes within the object. We've got all these little atoms in there, which all have their little magnetic fields. And within a domain, they're all aligned, but looking at the object as a whole, the domains are all scrambled at this point. But then as we move to the right and everything comes into alignment, that's where we end up with a noticeable, measurable magnetic field for an object. Right. So then once we've got an object that's magnetized, can it ever go back to being demagnetized? Absolutely. All we have to do is scramble up those domains again. We have a bunch of different ways that we can do that. Here are a few. One is we could confuse the magnet by throwing in another magnetic field in a different direction. So if I've got like a nice happy bar magnet and then I put it in a field that's going in a different direction, some of our domains will get confused as to which way they're supposed to go, and we'll scramble things up that way. We could heat up a magnet. That will tend to demagnetize it as well, because as the particles move faster, our electrons start spinning in different directions, and we end up with scrambled domains. And the last option, and my favorite, the one that I use the most often, is just to beat the crud, like physically, out of a magnet. Like actually hitting the magnet will tend to scramble those domains as well. Some of you may have experienced that if you drop a refrigerator magnet too many times on the floor, it will stop sticking to the refrigerator. That's because by dropping the magnet, you are scrambling those domains. So stop abusing your magnets. Okay, cool. So that's bar magnets. Let's jump over to electromagnetic fields and those current carrying wires. So just like with bar magnets, the magnetic field produced by a current carrying wire will also come in the form of closed loops. So we have left the realm of straight field lines. Everything circles now. Everything is in loops, okay? Now, if we wanted to predict the direction of that magnetic field produced by a straight current carrying wire, all you need is your right hand. We're going to use something called the right hand rule to predict which way that magnetic field is going. And so to do that, what you do is you identify the direction of the current and then place your thumb in alignment with that current. So if the current's going up, you have your thumb go up. If the current's going to the left, you have your thumb going to the left. Like whichever way your current's going, that's the way that your thumb is going, is in alignment with that. And then once you've done that, your fingers can only curl one direction. Like they can't, like maybe some of you are double jointed and can do terrifying things, but I can only really curl my fingers in one direction. My fingers then represent the magnetic field and show me which way that magnetic field is looping around the wire. Last big thing here. So we've talked then about the magnetic field produced by a straight current carrying wire. But the wire doesn't have to stay straight. We can loop it, all right? And if we were to loop this this current carrying wire, we can imagine then continuing to use that right hand rule to kind of see how all of the magnetic field lines produced by this current carrying wire continue to loop around the wire, all right? And when we do that, we end up with a shape that that looks kind of like this, where we've got those closed loops going all the way around our wire. And this should look familiar because this looks like the field of a bar magnet then, where we've got essentially this donut shape to our magnetic field lines. And so this turns out to be a really useful thing for us for creating these electromagnets, is looping this wire then a bunch of times to try to strengthen that magnetic field. And by looping this wire and creating a coil, we end up producing a magnetic field that looks like that of a bar magnet. Now, what we call this coil then, this current carrying coil, is a solenoid. It gets a special name. And so solenoids look something like what you see on your screen right there. They produce magnetic fields that look like the magnetic field of a bar magnet. Right. Now, looking at this magnetic field, where do you think then, since it's like a bar magnet, where do you think the North Pole and the South Pole of the solenoid are located? Well, what I see here is that the field lines are exiting the solenoid on the right, and they are entering the solenoid on the left, which means that the North Pole must be on the right, where the field lines are leaving the solenoid, and the South Pole must be on the left, where the field lines are entering the solenoid. Okay. Last check for understanding question. Consider these four statements about fields. Which of them is going to be true for all magnetic fields, including those produced by bar magnets, current carrying wires, and solenoids? Well, A can't be correct because straight current carrying wires do not have north and south poles. And C is not correct because electric fields don't form closed loops. And so D can't be right because two of those are incorrect. The only one that remains possible is B. The field lines always form closed loops. All right, that is your primer on magnetic fields and electromagnetic fields. Good luck. You've got this. Carpe diem. You're brilliant. Have fun.